Hello everyone, welcome back. In this lecture, we'll talk about stealing and defenses for supervised learning. Nowadays, machine learning APIs offer a broad range of services. Thanks to Google services, we can easily translate a given text, for example, from English to German. It can be done in a split second with a single click. We can also easily translate the whole web pages or documents. The ML APIs become a dominant paradigm for using ML models. ML services span language translation, language generation, or data annotation, or OCR, for example, that is for optical character recognition. OpenAI exposes its GPT-3 and GPT-4 models behind the APIs, and these models perform many NLP tasks, such as text generation. For example, you can use ChatGPT to recite the first law of robotics or generate a poem. It's fun to play with ChatGPT. It generates useful content like beautiful birthday wishes, but it's also sometimes scary how good this model is in performing plethora of natural language tasks. OpenAI codex system translates natural language to code. You can type a comment in the text box on the left-hand side and then see corresponding code on the right-hand side. Again, behind the API there is a large language model, in short LLM, that makes this service possible. Clarify AI went even a step further. They created a platform where other companies can deploy ML models in the pay-per-query setting, where users query their models and pay for answers. This platform exposes models for vision, NLP, and many other domains. Each of you can upload your model to the Clarify AI platform and get paid for the services that your models provide, such as accurate object recognition or maybe translation. In general, we observe that machine learning APIs become a dominant paradigm for using ML models. Behind the scenes, the creation of ML APIs that contain the models is a costly venture. There are four main factors that contribute to the high cost. First, it is hard to collect and clean the data, especially in the case of financial or medical domains. We also need to label the data. For example, to label 1 million images for a popular image dataset using Amazon Mechanical Turk, it costs more than $170,000 if we assume that we rely on a single label per image. However, in many cases, we also need more than a single label per image from a single person who labels these images, so the final cost is usually much higher. Next, we also need to hire ML experts to tune parameters for these models. And finally, expensive hardware such as GPUs, TPUs, or many CPUs are needed for training and inference. For example, it was estimated that a single training run of GPT-3 model costs north of $12 million. Now, to be more precise, the stealing process for supervised models lowers the labeling cost. So this is because we use a machine to label our data instead of paying a human labor. In contrast, for the self-supervised models like GPT-3, assuming that we have no instruction tuning and no additional reinforcement learning for human feedback for this model, the model is trained on unlabeled data, so the cost of labeling is zero. So the main cost for these other types of models goes into the training itself to update the parameters on a humongous amount of data. In the next lecture, we will focus on the second type of models called self-supervised models, which are trained on data without labels. However, in this lecture, we are focused on supervised models that are trained on labeled examples. So to emphasize this point here, for the supervised models, the main cost is in data labeling, which, for example, in the case of ImageNet dataset, costs more than $170,000. If we want to train a model, for example, ResNet 50, on this data, the training the model costs roughly $358. So the cost of the training of the model itself for supervised models is much lower than the cost of labeling. So again, the main purpose of the attacker is to get the labeling at a much cheaper cost than hiring some human, than paying for a human labor. So let's go back to the setup when a user queries the API and receives the answers. The problem is that the querying party might be malicious with the goal of extracting the model behind the ML API. Model extraction is possible because the answers to the queries leak information about the model. In 2020, Microsoft published a survey where they analyzed many organizations and ranked model stealing as one of the most severe attacks against machine learning. So let us focus on. So this is the main table from the survey. The first column indicates which attack on ML is considered the most severe by a given organization. The data poisoning attack has caught the attention of many enterprises in this survey. It's also perhaps because of the cultural significance of Microsoft's Tailbot. So to recall, in the first lecture, we gave an example of machine learning model being released in adversarial setting, and the model can interact with explicitly malicious users. So back in 2016, Microsoft released a bot called Tay. It started nicely and had many followers. However, it caused subsequent controversy when the bot began to post offensive tweets through its Twitter account. And it caused Microsoft to shut down the service only 16 hours after its launch. Tay's misbehavior was caused by mimicking the deliberately offensive behavior of other Twitter users. So this incident highly influenced the thinking about what data is fed to the ML models. If the data is poisoned, then it can substantially change the model behavior, not only that model underperforms in a given task, but also can be potentially harmful. So from this survey, I can quote what a medium-sized financial tech company indicated. So they were saying that we use ML systems to suggest tips and financial products for our users. The integrity of our ML systems matters a lot. We are worried about incorporating recommendations like that to be attacked as the same way as the Tay bot. So later in this course, we will also touch base on the aspects of model poisoning. However, in this lecture, we will focus on the second most difficult aspect is how to prevent model stealing. So organizations care most about the attacks that can lead to potential breach of privacy. As one of the banks from also the surveys indicated was that they want to protect client information, employee information used in the ML models, but currently they still don't have a clear plan in place. And the model stealing that we are discussing today is also a big concern, since it can lead to loss of intellectual property. A large retail organization said that they run a proprietary algorithm to solve their problem, and it would be worrisome if someone can reverse engineer this algorithm. Interesting outcome from this survey was that also adversarial examples in the physical domain, where adversary makes a small, usually imperceptible changes to fool the model used behind the API. For example, such a model on in a self-driving car. So this attack resonated with the respondents for this survey, but did not rank very high on this list. However, one reason why this might be the case is that organizations that actually were analyzed by Microsoft in this survey, they don't really have the physical component like cars or drones. So overall, from this very broad survey, we observed that model stealing is really one of these key concerns. And here in this lecture, we will talk more about how to really think about model stealing, what are these real threats, and how we can potentially defend the models from being stolen. So the first paper on model stealing was published in 2016, and it showed that model extraction attacks can subvert model monetization, meaning that if somebody steals our model, then the model can be exposed by somebody else, and then we, for example, don't receive the queries from the clients, and then we don't receive monetary gain for our service. Also, if somebody steals the model, it can also violate training data privacy and further facilitate model evasion. So what can happen is that it can be treated as so-called reconnaissance attack. So somebody can steal the model and then use the model later on to carry out other attacks on the model behind API. One of these examples is that somebody might just generate adversarial examples on the stolen model, and then these examples in this situation would transfer much better to the model behind the API. And this is really important, for example, if we talk about security applications such as spam detection or fraud detection. So in such cases, ML models are really critical, and then we have to really protect their confidentiality. So adversary can learn the model and then can also evade detection and then succeed in a given, let's say, financial fraud. So through local experiments and online attacks on two major providers, back then in this paper the authors use BigML and Amazon providers. Through these examples, the authors illustrated that it is efficient and then applicable to steal the models and exploit common API features such as availability of confidence scores or the ability to query arbitrary partial inputs. So for instance, in this table that we show in the slide, these are the results of model extraction attacks on ML services, Amazon and BigML. For each target model, the authors report the number of prediction queries made to the ML API in the attack that extracts, and this is very important, 100% equivalent model. So the attack time here is really low, it's 70 seconds or 149 seconds, maximally is like 2088 seconds, and still, what is really important is that this attack time is still primarily influenced by the service prediction latency, which was roughly 100 milliseconds per query for Amazon and 500 milliseconds per query for BigML. So note that in this setting, the researchers trained the models on their own and deployed the models to the given service. This was also disclosed to the affected services back in 2016, and these results show that the stealing is very effective with as few as, for example, 650 queries within 70 seconds, and you can steal the model behind the API. So furthermore, authors of this paper also explored initial potential countermeasures to these attacks. So the most obvious way how to limit the possibility of attacking the model is to restrict the information provided by ML APIs. So building upon prior work from learning theory, the authors showed that the attacker that only obtains class labels or adaptively chosen inputs may launch less effective and also potentially less harmful retraining attacks where a copy of the victim model is trained on the attacker's end. However, note that such an approach limits the utility of the API for the legitimate users. The next attempt how to protect models from being stolen was to round class probabilities. So when the class probabilities are rounded to 4 or 5 decimal places after the decimal point, as for example done in a BigML service, this has no effect on the attack success. So attack success is still 100%. The attack is slightly worse if we round these values to 3 or 2 decimal places. But still, this attack vastly outperforms adaptive retraining using class labels only. And the other idea how to prevent model stealing is by using differential privacy that we also discussed in the previous lecture, and we, for example, used model parameters. However, it does not really help to prevent model extraction per se, since you could simply extract the model trained with the PhD. Interestingly enough, this paper was published in 2016, and in the same year, there was a paper actually published about the PhD. And the authors of this paper about model stealing just mentioned exactly the idea for the PhD. And later in the lecture, we will see how to apply these methods from differential privacy to really obtain some techniques to prevent model stealing. So specifically, we will show how to apply Pate to the model outputs to limit the information leakage from a given model behind the ML API. Finally, also the authors of this paper proposed that we could leverage the idea of ensembles, and this will be also covered in our lecture later on. And the main point is the attacker might obtain only an approximate of the target function, since the function is not expressed by a single model. So this is another recent example. So researchers from CISPA showed that training less than 50 model, which is in this case self-supervised model trained without any labels, costs north of $5,713, whereas stealing such an encoder costs only around $72. So this is 80 times less cost to steal the model than to train the model from scratch. So the stealing of such encoders is relatively inexpensive, since these ML APIs return a large amount of information. An attacker has this incentive to steal the model at a much lower cost than training the model from scratch. Taking into account how versatile and useful the ML services are and how important the problem of protecting them is, we will delve deeper into this topic. So let's start from the beginning. How do we use the ML APIs? Imagine that you have an image and would like to label it. You can send this image as a query to ML API, and the ML API responds with the correct label, in this case being a dog. However, the user who queries such an ML API might be malicious. So let's look at the ML API from this perspective. How to steal the model behind the API. So actually it's relatively easy. An adversary has to collect some unlabeled data. Then each of the unlabeled data items is sent to the query, to the ML API, and the API responds with low-dimensional outputs such as labels or softmax scores. Based on these queries and obtained labels, adversary trains a stolen copy of the victim model. What are the assumptions here? It is enough to have unlabeled natural data, even from a different distribution than the victim's training set. The architecture of the stolen model does not have to be the same as the victim's architecture. Additionally, APIs expose information about their models. For example, what data the models were trained on, what's model architecture, and this is released to provide more trust and transparency for the users of these APIs. So how can we steal models from ML APIs? We taxonomized attacks based on their assumption about the access to the data used for stealing. First, mixed-match extraction leverages techniques from self-supervised learning and assumes access to unlabeled data that are task-specific. Before we can understand the mixed-match based model stealing attack, we have to introduce the mixed-match semi-supervised learning algorithm. Mixed-match takes as input a batch of labeled data X and a batch of unlabeled data U. Usually, they are both of the same size. Then mixed-match produces a collection X prime of processed labeled examples and a collection U prime of processed unlabeled examples with guessed labels. We augment each labeled example. We also augment each unlabeled example, but in this case not once, but k times. And usually the k is set to 2 in mixed-match. Then we assume that we have a current model P trained initially only on labeled examples, and after the first round of mix match it is trained on the newly augmented labeled examples and the augmented newly labeled examples from set U that were initially without labels. So we use the current model to compute the softmax outputs from the augmented examples from the set U. And then we do the sharpening. We use the sharpening function to reduce the entropy of the label distribution. So we use the common approach of adjusting the temperature, here denoted as upper T. So P is some input categorical distribution. You can think about that as, for example, softmax output. And specifically in the mix match, P is the average class prediction over augmentations. And lowering the temperature encourages the model to produce lower entropy predictions. So let me show an example. So here we have on the left hand side code, and on the right hand side is corresponding output. So if we set the temperature to 1, the sharpening function does not change anything. The input is returned as the output. However, if we increase the temperature to, let's say, 100, then the output probability is almost uniform, which represents the highest entropy. When the temperature is very low, namely 0.01, then the middle highest value is almost 1, while the other values are almost 0, which is almost 0 entropy, and we know that the class 2 is the predicted class with 100% certainty. Mix match uses sharpening with temperature T equals 0.5, where the highest value is increased a bit to reduce entropy. So in the final step of the mix match algorithm, we combine and shuffle all the augmented examples and their labels. So we mix both labeled examples and unlabeled examples with labeled guesses. And the final step is to perform mix-up. So we compute the mix-up to interpolate between samples x sub 1, x sub 2, and their label distributions p sub 1 and p sub 2, and this is done in the following way. So first we take a lambda value from the beta distribution. So for simplicity, you can think about this as generating some random number from range 0 to 1. Then we take the greater value from lambda and 1 minus lambda. And the second line in the set of equations is to ensure that the generated x prime is closer to x sub 1 than to x sub 2. So just to give you this exact pointer, so here we choose the higher value from lambda versus 1 minus lambda, and the higher value is assigned as a coefficient to example x sub 1. And this is also because usually these examples, they come from the ground truth labels, from the examples that are actually labeled. So we assign also higher weight to these examples than to examples that actually are unlabeled and they have guessed labels. So here in this equation we interpolate between examples x sub 1, x sub 2, and in the next final line we interpolate between the probability distributions, so let's say softmax outputs for this example 1 and example 2. Okay, so with that we have the final part of the mix-match semi-supervised learning algorithm. So we have to compute the loss, and we find this x prime and u prime value using the mix-match algorithm. Then we compute separately loss for the x prime, so for the examples that are here also labeled with ground truth. And then we also use the another part of the loss to compute this loss for the examples with the guessed labels. And then we combine these two different loss functions Here we usually set this parameter lambda sub u to 100, but this is just a good starting point for this fine-tuning of this method. So with that, we can go back to the original stealing algorithm, which actually is based on the mix-match. Going back to the mix-match based stealing, it uses a small number of labeled points, where the labels are stolen from the ML API. It also takes advantage of an unlabeled set to achieve high accuracy. It assumes that we have access to the in-distribution data, meaning the same distribution as in the training set of the victim. An adversary collects labels for a part of their data set using the victim model. Mixmatch then applies many standard data augmentation methods such as random horizontal flips and crops, then leaves the class semantics unaffected. An augmented dataset is then generated involving both labeled and unlabeled examples, and their actual and guessed labels on which a model is then trained using a semi-supervised loss function. Then the guessed scores for the unlabeled examples are sharpened after averaging the softmax output from many augmentations. The final step is to use mix-up to interpolate between pairs of examples and their labels. There are many other ways how to steal the models. So the second stealing attack, which is also popular, is called Jacobian-based data augmentation. And this attack actually was used primarily as the reconnaissance attack, so to replicate the model behind the API, and then after that to perform in these scenarios search of adversarial examples on the replicated model. So Jacobian-based data augmentation is an attack strategy that starts with initial small seed dataset, and we also assume that actually this is in-distribution dataset, and then this initial set is iteratively augmented using these Jacobian-based augmentations. So this is the main point. You can also just give you some more details about that. So in this stealing process, at each iteration, a new sample is generated for each of the samples currently in our set, and we generate the new samples using the Jacobian of the model against the inputs. The Jacobian matrix is the gradient of loss for each class with respect to every component of the input, and this is used to extract sensitivity direction. And the Jacobian is a generalization of the gradient to vector functions. After this augmentation step in the algorithm, all samples in the set are labeled by the victim model, and the model then is retrained on our end. So this is how this attack is performed. There are many other attacks. Very famous ones are especially knockoff or also copycat attacks. And the main point about these attacks is that they don't assume any access to the in-distribution examples, but for their stealing process, they use out-of-distribution data to query the victim model and then create a labeled data set from these queries and the obtained answers. So after this, after we obtain labels for these out-of-distribution examples, we train the stolen copy, which we assume that has similar architecture to the target model, and also we use this surrogate dataset. And really the most surprising part of knockoff nets is that the model stealing with auto-distribution data works very well and creates a performant stolen copy. So one hypothesis is that the features of the stealing dataset are also extracting the useful features from the victim training set. So this is still an active venue for research to clearly show why these types of attacks really work. But this knockoff attack is actually very widely used, and then it's really interesting to consider for as one of the first, I think, very cheap attacks to run that can also bring us surprisingly high functionality, high performance for the functionality of the stolen copy. Let's move on. So finally, there is also attack which is called data-free model extraction. This attack uses synthetic queries generated from a GAN model. So it's generated with adversarial networks to query the victim model. And the main step in this attack is the approximation of the gradient to update the parameters of the GAN model. And here the main point is to approximate the gradients, and then it allows us to query the victim model and improve over time the queries that actually generate from our GAN model. And here important also aspect is that the student model and the victim model, they act as discriminators for the generator model, allowing the student model to be trained over time. And the parameters are updated based on the derivative of the loss concerning the student model. For the gradient, we also use a similar approach, but compute the approximation of the loss concerning the generator for the update step. The main point here for this attack is to just remember that it works without any previous dataset, but it generates this dataset synthetically using the GAN model. So, having described the main ideas behind the attacks, we compare them with respect to the data or query type used for the attack, number of required queries to extract a high-performing model, and the final goal of the adversary. In general, we observe that the closer the data type used by the attacker to the original training data used by the victim model, the fewer queries are required to carry out the attack. The mix-match attack is the best performing one with very few queries run against the ML API and the high accuracy of the extracted model, mainly due to the abundant and efficient usage of the task-specific data. At the other end of the spectrum is the data-free model extraction with only the synthetic out-of-distribution data used for stealing. It requires many more queries than mix-match. The main goal of most attacks is to create a model with a high task-specific accuracy. Accuracy is similar to fidelity with some small differences. For instance, the adversary who optimizes for fidelity wants to match all predictions to the victim model independent of them being correct or incorrect. It is also worth noting that the mix-match attack has a high upfront cost since it requires collection of in-distribution data whose distribution matches the distribution of the victim's training set. To the defenses. So, having discussed these possible attacks, we now can also taxonomize defenses into another 4 classes. So, current active defenses either truncate the outputs or perturb them to poison the training objective of an attacker. So here the idea is that we, as the defender of a given model, we return the answers to the querying party, but we perturb the answers in some specific way, and usually the cost of perturbing the answers is quite high. So the fact that we want to disable possibility of the attacker to create a similar copy of our target model is quite a difficult objective. So we have to put quite some effort to be able to still return useful answers, for example, to benign users, but at the same time to create answers that would make the possibility of copying the model really cumbersome or difficult. So there are such methods which propose this aspect, and I think this is a really good way how to tackle the problem. However, one of the main issues here is quite high cost of running such a defense. There are also so-called passive defenses that use a difference in the distribution of queries made by the attacker and legitimate users. So this is one of these examples how one can imagine passive defense, but in principle the idea is to first gather a few queries from a given querying party and then analyze what are the queries. So one way how to do it, this analysis of the queries, is to just check what's the query distribution. And in this specific defense, this defense stop answering queries for a given user if the defense detects that these queries are adversarial. So in this case, we have here example of this method. So if we have here user who is legitimate, usually these user's queries, they follow standard normal Gaussian distribution. However, if the user is an attacker who wants to extract the model, so in this case they actually applied this Jacobian-based data augmentation attack, then the query distribution is much different from the normal distribution, and then this is an indicator that this user is potentially malicious. Okay. There are also reactive defenses. So the main idea behind these defenses is that we don't protect the model when the model is exposed through the API, but post factum we want to check if a given model actually belongs to us. So these defenses are applied after the attack has happened, and they are used to detect if a model was stolen. So for example, one of these methods that is used as a reactive defense is called dataset inference, and this method leverages differences between the behavior of an ML model on private versus public data samples. The main idea behind this defense is that the training data that we use in our own model, in our so-called target model that we want to identify as being our own property, our training data, we assume this is private, and this training data can act as a signature for our model. And here in this specific defense, we leverage the differences between a given data point and the boundaries between classes. So here we have two cases. Here on the left-hand side, we have a training dataset. On the right-hand side, we have test dataset. Here, X is a training data point, and then we measure the distance between this data point to decision boundaries. So this distance is observed to be much higher for training data points than for testing data points. So for this test data point X, distances between the data point and decision boundaries between classes are much, here in this case for test set, are much smaller. And where does it come from? Why do we observe this effect? And then here it occurs that if we train the model, then we really want our model to stay within, in this case, class A, and we want to push this data point further from other decision boundaries for class B, class C, and class D. So in this case, this data point X indeed stays probably much further into the area for class A than for other classes. However, for test data point that has not been seen during training of the model, it's not the case. So we've never pushed this data point to be further from decision boundaries. This is why, on average, data point X has a smaller distance to other decision boundaries. And you can think about this defense as being some derivative of membership inference. In membership inference, we consider only a single data point being either in the train set or not. Here, for this defense, we can use our whole private training set to check on average across all the data points if we have this property that our train set is farther from decision boundaries than the test set. And in the next lecture, we also will cover more of this defense, and we will extend it to other types of models. So here, this defense is solely for supervised models. The next lecture, we also cover how we can extend this defense to self-supervised learning models. And finally, in today's lecture, we also focus on the proactive defenses. They are also called active defenses. Idea here is that we make model extraction more difficult by requiring users to complete a calibrated proof of work puzzle before they can read model predictions. And the difficulty of this proof of work puzzle depends on privacy leakage, which is estimated from queries from a given user, and this measures with this is measured with tools from differential privacy. So this defense, in principle, wants to make sure that if somebody can incur more information from our model, then this person should also pay higher cost for queries to the model. And then the main point of this defense is that it does not degrade the quality of outputs. So we never return some form of perturbed outputs as other active defenses. This defense acts actively, so it's not reactive. It just acts as the model is happening. And also it can be per each query. So we don't have to wait until we gather many queries to start this defense. So maybe let me give you some more details about these different defenses, and we can compare them more systematically. So here we compare these defenses based on these features, if they are active, if they still return clean answers or not, and if they can protect against sibils. So why do we here have also this new concept of sibils? Actually, it's a very important concept, and then it's called Sybil attack. So Sybil attack is the attack where an adversary creates many fake accounts and query the API from many of them simultaneously. So let's consider these three features in terms of the attacks that also we talked about in the previous slide. So the passive defenses that try to differentiate between distribution of queries from legitimate users versus adversaries. These defenses stop answering queries if they detect the user's queries deviate from the normal Gaussian distribution. So these defenses are not active. They do not protect against Sybil attacks because an adversary might query from different accounts, and even if one account is stopped, then other accounts can be still leveraged to steal the model. But on the positive side, this defense provides clean answers. So we never perturb answers, and we never make legitimate users to suffer from our defense. The second here defense, which is output distribution, output perturbations, is active defense. So this type of defenses, they perturbed the outputs to poison the objective for training for the attacker, and these defenses they have this trade-off between higher robustness and lower and the utility for the outputs. So in this type of defenses, the more we want to protect the model, the more the legitimate users have to suffer because we lower the quality of the outputs. However, if we lower quality of this defense, meaning that we have lower robustness of the defense, then of course also legitimate users have higher quality answers. So there is this trade-off that we have to operate within. So these defenses, of course, are actively. They change, for example, the outputs for every single query. They also protect against Sybil attacks because they act per query. But the biggest drawback is that they harm the performance for legitimate users because they don't return clean answers. And then this other defense, active or proactive, where we increase the extraction cost depending on how much information leakage a given query incurs. This defense actually is at the same time active. It returns clean answers, so never perturbs the answers, so that the legitimate users do not suffer from this defense being present. And then also this defense acts against sibils, since we can measure the information leakage per query, and then per query cost a given user more or less. So saying that, we have to here emphasize that proactive defense is the only defense that works as the stealing process is happening, and it does not degrade the quality of outputs, and at the same time protects against Sybil attacks. So in the rest of the presentation, we'll focus primarily on this active defense. To give you a bigger picture, we'll focus primarily on active and proactive defenses. Also, in the later slide, second lecture about stealing and defenses for models, we'll also talk more about how to resolve ownership, so how to find out if a given model actually belongs to us. In the next lecture, in general, active defenses act as the stealing attack is happening, and they aim at deterring an adversary. So just making sure that the stealing of the model is much more expensive. And then the second bigger type of these defenses that resolve ownership, they act after the attack. And also other types of this defense, apart from based on dataset inference, are also, for example, watermarking techniques, which embed into the victim model the watermark during training. And then if an analyzed suspect model also contains this watermark, then we can mark such a model as being stolen. The difficulty of active defenses stems from the fact that they need to differentiate between legitimate users and adversaries. However, if successful, then they can prevent the attack as it's happening, instead of inspecting models post factum after the models were stolen. Current active defenses perturb the outputs to poison the training objective of an attacker. This means that the perturbed outputs make the training of the stolen copy much more difficult. At the same time, these defenses harm the performance of legitimate users. These defenses exchange higher robustness for lower quality of outputs for legitimate users. As I mentioned, we can just use defenses that are so-called proactive. It's different type of active defenses. They just increase the attack cost. And in these defenses, we trade robustness for higher cost. And then we can not only just, for example, send a puzzle for a user to solve the puzzle, but also this defense can, for example, require users to do some work or spend some time on some computation, or prove that a given worker has some disk space or money to ensure that a given user has to pay higher cost with the higher leakage from our protected model. So these proactive defenses enable us to trade higher robustness of a model for other resources, such as time. For example, that we have to, as a querying party, have to prove that we had to wait on a CPU some amount of time. It's so-called proof of elapsed time, or proof of disk space, or that we also have to pay more for the queries before we can get answers. And then this defense works with the same effect for any form of outputs, including labels, softmax scores, or logits. And then we can now delve deeper into how this defense performs. So we want to increase the attack cost for malicious users, but the question is how we can identify which of these users are malicious. And the main insight of this method is on how to distinguish between these benign and malicious users. And in principle, each of them sends some queries, and we have to really verify based on these queries which of these users are benign and malicious. And to detect a malicious user, we estimate information leakage for each user. So by the definition, an adversary who wants to extract model wants to extract as much information from the API as possible. So users who incur much more information from the API than legitimate users have to, in this defense, pay much more for the access to the API. So first, I will present an overview of this defense, and then we will zoom in on the individual components. So first, let's formalize a bit more. So here we assume that adversary collects some unlabeled dataset, then he or she sends queries to the API. In our proactive defense, the first step is to estimate the information leakage a given query incurs from the victim model. And the goal is to set higher costs for queries that incur more information leakage from the victim model than for the queries that actually don't incur that much information. So this step will be discussed very soon based on the also privacy methods. Once we estimate the information leakage, we generate a puzzle whose difficulty is calibrated using the estimated query cost. So the puzzle can be of different forms, and here by default this is based on the proof of work. So next, a user or an attacker has to solve the puzzle and send the solution back to the server. So this step increases the cost of model stealing. The server then verifies the solution. You can think about this step as the CAPTCHA, where users have to, for example, find which of the provided images represent a flower. In the case of the access to ML APIs, users, potentially malicious users, have to solve a puzzle which increases the cost of stealing. Then if the solution is correct, we return the label back to the querying party. Now let me zoom in on how we estimate the information leakage. Let us consider the victim model, which for the query of a cat outputs probabilities per label. The highest probability is assigned to the label of a cat. The second highest probability is for the label of a tiger. The information leakage from the model can be estimated using the margin leakage, where the cost is equal to 1 minus the gap between the probability of the model of the most probable class, in this case for a class 2, and the probability of the second most probable class, which is in this case class 4. If the gap is large, this means that the model is confident about the prediction and the margin leakage is low. On the other hand, if the gap is small, so the model is not confident if the input query represents a cat or a tiger, then such an example is probably close to a decision boundary between these two classes. An adversary might learn more about the model, so for this case the margin leakage is high. We also use the standard entropy metric, where y sub I ranges over all possible classes. The higher the entropy of the softmax scores, the higher the information leakage. So here entropy is standard entropy definition, which is the average message length using the best possible code. So we basically here just leverage standard metric from information theory. Finally, our main metric is based on the privacy leakage, which is proportional to the probability that the noisy output of a privacy mechanism is different from the predicted label. So this goes back to the Pate mechanism that we discussed last time. To measure the privacy leakage, we use tools from differential privacy, in this case the privacy cost estimator from the Pate framework. In our experiments, we showed that the privacy metric gives the most accurate estimate of the information leakage. And now let me elaborate more on this privacy leakage estimation. Let us recall the last lecture on differential privacy frameworks for machine learning. Pate is one of the two, apart from the PhD, differential privacy approaches to ensure that the data used to train the machine learning models remains private. First, we can create the ensemble of models behind the API, as suggested by the first paper on model stealing. Then we can use Pate to measure the per-query privacy leakage. Pate creates teacher models using the defender's training data, and predictions from each teacher for a query Q are aggregated into a histogram where n sub I indicates the number of teachers who voted for label I. The privacy leakage, denoted as cost of query Q, is proportional to the probability that the returned label is different from the argmax of the softmax output. Intuitively, the higher the consensus of teachers, the lower the privacy leakage. So if we want to expose only a single model behind the API, then instead of standard Pate framework, we can use the so-called private KNN framework. So this is another version of the Pate framework, where instead of creating many teachers, the data points from the training set act as teachers. For a given query, we use a feature extractor that determines what are the data points from the training set that are the closest to the query, and then the labels of the data points that are the closest are aggregated in the histogram instead of using the teacher votes. And you can learn more about this approach in this paper about private KNN that we also just indicated here at the bottom of the slide. So using private KNN and based also on this concept of the nearest in the embedding space neighbors from the training set, we can use this privacy estimation from private KNN for a single model behind the API. So just to recap, the main point for this method is that instead of having a single teacher for this part of the partition, we just compute what are the nearest data points that we can actually use labels from to create the histogram, and then from the histogram actually we can just proceed as with the standard Pate framework. Okay, so for now we covered how in this defense method that is proactive we can estimate privacy leakage using Pate framework. Now let's move on to the next part. So we go back to the overview of our defense, and we'll zoom in on the generation of the puzzle. So how can we really find the cost for a given user is covered with estimation information leakage, and then the second part is that once we estimate this information leakage, we have to generate a puzzle whose difficulty depends on this estimated value. So for the generation of the puzzle in our defense, we use our binary version of the Hashcash algorithm. The initial version of Hashcash was for the hexadecimal representation, but we changed it to be the binary version so that we can have more fine-grained control over the difficulty of the puzzle. So a server sends a challenge string S to a client. So in the blue frame we have an example of such a challenge string S. And then we use then to solve the puzzle, the client has to find a suffix X that can be appended to the challenge string S, so that the message digest, the hash of S with appended X, has at least a specific number of leading zeros. In the red box we have an example of such a suffix S. The only way to solve the puzzle and find such a solution by a client is by using brute force search. So we apply the brute force approach because we do not want any attacker to circumvent our defense. We show the solution in the binary form, and then the question is really like, okay, once we have this puzzle, what is the computation cost that is incurred for a given user? So here in the figure on the right hand side, we present how much computation time a client has to spend. This is on the y-axis as the function of the required number of leading zeros, zero bits in the binary hashcash algorithm, and this is on the x-axis. So in general, the more leading zeros are required by this puzzle, the more difficult is to solve it, and the more time has to be spent by the client to solve it. And this actually cost grows exponentially. And then after this step, we have to also calibrate the difficulty of the puzzle using the information leakage incurred by the user's queries. So first, we set the query cost for legitimate users as a reference cost. A legitimate user is assumed to be one who sends queries from a similar distribution as distribution of the dataset used for the training of the victim model. And also these queries are sent in random order. So the privacy cost for this user is shown as the solid yellow line in the graph. And next we measure the cost of queries for a given user, and what we observe is that the standard model stealing attacks such as Jacobian, copycat or data-free model extractions, they incur much higher information leakage than legitimate users. Finally, we map the information leakage to the puzzle difficulty. So the higher privacy deviation of a given user, the more difficult puzzle is sent to the user. Finally, we also give you some final results from this defense. So just to show how this defense performs. So in this graph, we compare the accuracy of the stolen model shown on the y-axis against the time in seconds to run the queries presented on the x-axis. Note that the x-axis is the log scale, and we show results for both before solid line and after our defense is applied, which is dashed line. For legitimate user, the increase in query time is a maximum of around 2x. Next, we show that the application of this defense, proactive defense, against the copycat attack, and the increase in the attack time for copycat is even up to 100 times. So this really shows that this defense is very efficient. So with that, we finished the part of the lecture which is on stealing and defending supervised learning models. In the next lecture, we will cover how to steal and defend self-supervised learning models that are actually learned on unlabeled data samples. With that, thank you for your attention. You can also consult our references to learn more about these specific topics. And thank you for your attention, and see you next time. Thank you so much.